Today we're looking at, do we even have an inverse in the first place? We've been looking at a function and its properties. We've been looking at how to find an inverse. But now we're asking a question, does it even have an inverse in the first place to find? So let's take a look at this example here. We're going to be looking at the parabola x squared. So here's my table of values. You can see every input has exactly one output. Even if the outputs are the same for some of these inputs, that's okay. But there's exactly one output per input, and that passes the vertical line test. So we've talked about that previously. So the question is, does it even have an inverse? Now, we're going to be analyzing this further down the page by asking the question, is it one-to-one? So we'll be talking about that in a moment, but with the tools we have up to this point, what we're doing is we're going through the process of finding an inverse, which is not what we're going to be doing in the examples to come, but using the tools that we have, we would find an inverse by swapping the x with the y, swapping the input with the output, solving for the y, and then seeing if we have a plus or minus. We have a plus or minus, which means there is no inverse to be found at all. This is what its graph would look like. If we were to use an input of 4, we would get an output of plus or minus 2. Well, that's two outputs, and that's not going to work for us. If we were to graph this, we would have the positive and the negative, that's our plus or minus, of the root x, and so that would fail the vertical line test. So this inverse does not exist. But we were looking at this by identifying if we had a plus or minus. And that's kind of the key piece to what we'll be doing today. You can also see with the table, we almost have this pattern of exchanging inputs with outputs. This output of 4 is the input of 4. This input of negative 2 is also here as well. You see the negative 2, except that we have the plus or minus because of the process that we're looking at. So we want to take a look at a system that can handle the question, does an inverse exist, without actually finding the inverse itself, because in some cases there is no inverse to be found. So before we get to the algebra nature of this, let's look at some tables. And to do that, I'm actually borrowing the tables that we saw on the very first page of our notes. We're going all the way back to day number 1. And on this page here, we were introducing a function and how to determine if we are actually seeing this pattern of each input has exactly one output. Well, if we're looking at this now from the perspective of an inverse, does an inverse exist? We're going in reverse order. We're saying, does every output have exactly one input? So you want to think of it in this direction. We're going from outputs to inputs to ask the question, do we see the pattern of an inverse? So inverse question mark is what we're asking. So in other words, if I were to take this 7, does it pair up with exactly one output? 4. Yes, it does. So we're kind of going in this order here. If I plug in a 4, out comes an input of 4. So if I plug in a 7, out comes a 4. If I plug in a 2, out comes a 3. If I plug in a negative 9, out comes a 3. When we were analyzing this earlier to determine if it was a function, we said it is not a function because the input of 3 has 2 different outputs. But now we're going backwards. If I have an output of negative 9 or an output of 2, my input is 3, and that's okay. We can have the same input as we're analyzing this in reverse. So yes, this does show a pattern of an inverse. Same with this example here. In this table, this was originally not a function because we had the same input giving us 2 different outputs, but now we're going backwards. I have an output of 11, and that gives me an input of just one input of 2. Here's an output of 10, and that gives me an input of 2. It's okay that the inputs are the same because we're going in reverse order. The question is, how many inputs do I have? When I have an output of 10, I have exactly one input. So yes, this is an inverse. So if we were to take a look at this mapping diagram here, we said this is a function because every input has exactly one output. It's okay if several inputs have the same output. The point is that there's exactly one output. But now to determine if it's an inverse, we're going in reverse order. Here my output of 3 has an input of 2 and, wait, there's a second input? Yeah, so this is not an inverse. And so we're thinking of this in reverse order. Does every output have exactly one input? So that's what we're doing when we're looking at a table of values or a mapping diagram. But we don't always have a table of values or a mapping diagram. Sometimes we just have a function, and we want to analyze the function without going through the work of finding a table of values, and it's, if there's an inverse or not. We want to examine this algebraically. And so we're going to do that here. And that's what we call testing to see if a function is one-to-one. So we're going to read this. It won't make sense at first, I guarantee you. We're going to sort of talk you through it here in a moment with some extra details before we get to the examples down here in example 1 or 2. So when we're asking the question, does it even have an inverse? Well, that's another way of asking the question, is it even one-to-one? One-to-one means that it is both a function and an inverse at the same time. That means every input has exactly one output, and every output has exactly one input. So if it's one-to-one, that means it's both a function and an inverse. So if we can test, is it one-to-one, then that means yes, it will have an inverse after all. Another way to talk about this one-to-one, you see this here below the box. Another way to say this is every input has exactly one output. That's what I was just saying a moment ago. That describes what a function is. And every output has exactly one input. That's describing what an input has. So if it has both of these qualities, we call that one-to-one. So what we're going to do is we're going to run this test. We're going to take the same function. That's what the notation with the letter F means. But we're going to use what we think might be two different inputs. Notice we're not actually using numbers. We're just using letters A and B. Because if this works with letters, it will be guaranteed to work for numbers as well. So we're going to plug in two different inputs, but the function notation is communicating that's the output. So think of this is the answer when you plugged in the A. This is the answer when you plugged in a B. So we're thinking maybe we have two different inputs, but the answers are the same. The outputs are the same. The equal sign there means this output is the same as that output. That's what a function does. You plug in one answer and you get exactly one output. But now the question is, in order to have an inverse, I can't have two of these. I have to have exactly one input for every output. So what we're looking to see is, did I really have two different inputs in the first place? Or are my inputs really one and the same thing? So we're going to look to see if we have this pattern of A equals B in our algebra work. And if we get the result of A equals B, that is implying we never had two different inputs in the first place. They were really the same input. That means there's only one input for each answer. That means each answer has only one input. And that's what an inverse is doing for us. So it will be one-to-one. I know that's not making a whole lot of sense there. Let's see if we can go through an example here. In example 1 and 2, we're going to determine if the function is one-to-one, which is really the same thing as determining if the function has an inverse. So we can ask the question either way. It's the same process. This is telling us what to do. Take the function that you see and plug in A. Take the function you see and plug in B. Set them equal to each other. So we have this square root of x plus 1. Now, there's its graph, so we can see visually what it looks like. But the concept is we can do this without having to rely on any table or any graph. And we're looking to see, do we have an answer that matches this pattern or not? So the function is root x plus 1. This is where the input goes. What do you plug in? This is telling you what to plug in. So we're going to plug in the A right here. So it's a root A plus 1. Now that represents the output with an input of A. On the right-hand side, this also represents the output but this time with an input of B. So we are thinking that our outputs might be two different numbers and we're getting the same, we're thinking our inputs might be two different numbers and we're getting the same output. So let's see if we can solve for A. I'm going to move my constant terms to the other side. They cancel out, of course. Let's square both sides to eliminate the square root. And so we were starting off by thinking we had two different inputs, but no, actually we don't have two inputs. There's only one input. If A equals B, that means they are the same. And if they're the same, that means you have every input has exactly one output, and every output has exactly one input. We only have one input because A and B are equal to each other. They're really the same thing. The point is, when you see an A equals B, that allows you to conclude that, yes, this is one-to-one, which means that it does have an inverse, and we can find it if we wanted to. Graphically, we give this a horizontal line test, and that tells us if we have an inverse. So the vertical line test determines if it is a function, but we are asking, does it have an inverse? So you give it the horizontal line test, and yes, it crosses only in one spot, so that means every output has exactly one input. Here's another example. Here's our parabola x squared plus 2. So again, there's the graph of it. You can see it passes the vertical line test, so it is a function, but it will fail the horizontal line test, right? So if you do that, you can see it's crossing at two spots, and that means there is no inverse. For every output, I'm getting two inputs, two x coordinates. So let's see how that works out algebraically. So here's what we do. We take the function and we plug in a in place of the x. It looks like a squared plus 2. We want to know if we set that equal to b squared plus 2, will we get this pattern of a equals b? So I'm going to subtract 2 from both sides to eliminate the constant terms. We have a squared equals b squared. Solve for a, we take the square root of both sides. And when you take the square root, don't forget that plus or minus. So a equals plus or minus b. Uh-oh, it doesn't match the pattern we're looking for. That plus or minus is telling us we don't have the same input. There really are two different inputs. That's what we're seeing here. Here's an input, whatever that x coordinate is. Here's an input, whatever that x coordinate is. There are two different inputs. Here, let's just put it here so it's easier to take a look at. Let's just say that's positive 3, comma, some output, and this is negative 3, comma, some output. Right? We have the exact same output because it's the same height, but we have two different inputs, a positive and a negative. So we really have two different inputs, so it's not an inverse, because an inverse has to have exactly one input, and you can see we're working with two different inputs in that case. That's how we show it algebraically. So let's just look at a few other variations on the next page. We're giving these graphs the horizontal line test to see if it's one-to-one. So let's get this in our standard form by moving the term of x in front and the 4 in the back. But we have to have a negative 1 factored out so that we can create a positive x. That's the standard form. So this is our b, this is our h. And so that means we're going to have a reflection across the y-axis, so a side-to-side reflection. And this is my horizontal movement to the right, not to the left, but to the right 4. So 1, 2, 3, 4. That's my termination point. There's my first critical value. There's my second critical value as it extends leftwards and upwards. So give that the horizontal line test, and it passes. So we could say, yes, it's one-to-one, which means it's already and automatically a function and an inverse at the same time. So all of these are yes. Jump down to example 5. I want to do that one here with the time we have. I want to take a look at this function with the x plus 2 quantity squared. There's my value of h, so that's a leftward movement of 2 spaces. There's my vertex. So this is the outline of the parabola. I'm just dotting it in right now. That would fail the horizontal line test. This is restricting the domain. If we say x is greater than or equal to negative 2, that means we're only using some of the graph, not all of the graph. And because we're restricting the domain, that means we only have part of the graph. That means it passes the horizontal line test. So yes, it is 1-to-1, which means it's a function and it's an inverse as well. So if you had the parabola as a whole, it would fail, but with the domain restriction eliminating half of the parabola, then it passes. And we're going to wrap up our notes right here.